Today so last time I talked about the matrix completion. Today I want to tell you how we can relate it to free resolutions, and the thing is to look at the cones that Greg also introduced, so sums of squares and non-negative polynomials on projective algebraic sets. So in this talk I will fix X in some Pn, and I want this to be a real algebraic set. So defined by real equations, but I don't insist that it be irreducible. That's what I want to say. Okay. And then Greg already introduced. So we're looking at quadratic forms on this X, and Px is the cone of non-negative quadratic forms. Quadratic forms on X, and this is a convex cone in the coordinate ring of X in degree 2. So R in this talk will always be the coordinate ring of this real algebraic set. So I don't know, just to all right. And then there's a second cone, the sums of squares of linear forms, which is contained in the non-negative polynomials. Of linear forms. And if I square linear forms, I also get a quadratic form. So these are my two convex cones in this vector space. So Greg talked about the irreducible case. So you may ask, when are these two the same, for example, right? So if X is irreducible and a few other things, so you want it to be non-degenerate, that I also want throughout the talk, and you want a dense real point, dense real points. Then sigma x is equal to px if and only if the degree is equal to codimension plus 1. Okay, so that's true in the irreducible case. In the reducible case, you run into trouble when you want to compare the degree to the codimension. So the inequality that the degree is at least codimension x plus 1 is not true anymore. If you take, for example, 7 lines in P3, will have degree 7, but codimension 2. So there is no okay. And if you take 2 skew lines, degree is 2, but codimension plus 1 would be 3. So there is no inequality anymore. So, but we care about reducible things for various reasons, and one reason is the matrix completion problem, which I will recall. And that's the case of a coordinate subspace arrangement defined by quadrics. Subspace arrangement. So we want defined by quadrics, that's a restriction. Cut out by things of degree 2. But that's, from our point of view, a natural restriction to make, because these cones only see the degree 2 part of the coordinate ring. So if we have higher degree equations defining our x, then we are not looking at the right cones, possibly. Okay, this anyway corresponds to the matrix completion problem, so let's recall how that went. So I claim if you write a quadratic form Q in the coordinate ring as a sum of squares of linear forms, and that's the same as completing a matrix, a partially specified matrix, symmetric, to a PSD matrix. So I will do this by example. So what I did in the last talk is I drew graphs to encode these subspace arrangements. Maybe let's do an example and the general setup at the same time. So suppose G is any graph. Example 4 cycle. So we have to label vertices, but that's not so hard. So then from a graph, I write down a quadratic monomial ideal by collecting non-edges in the graph. Right? So in this example, there are two non-edges. You produce two monomials, x1, x3, and x2, x4. And the thing that they define, I call xg. This, I claim, is a coordinate subspace arrangement defined by quadrics. And in this example, you will get 4 lines in P3. Okay, so how do you get the 4 lines? Any ideas what the 4 lines are in P3? So this ideal defines 4 lines in P3, okay. So if, you know.
x1, x2 equal to x1, x4, 3x2, 6x4.
Okay, pick a variable from each monomial, set them to 0. So you have 2, but we're in projective space, so they define 4 lines in P3. The 4 coordinate planes, basically. Okay, so in general, this will be a coordinate subspace arrangement. May not be completely obvious at this point that this is true, but this will always be an arrangement of coordinate subspaces. And you can tell from the graph which one it is. So secretly, this is the Stanley-Riesner ideal. So what happens is that the subspaces in the subspace arrangement correspond to complete subgraphs. So the lines, right? So I have the line 1, 2, for example, spanned by the first 2. So that's a complete subgraph. And there are 4 complete subgraphs. So these are the 4 lines, and in general, that's what happens. So the complete subgraphs gives you the coordinate subspaces, and this is their defining ideal. And you can go both ways. If you have such a coordinate subspace arrangement, and you know it's defined by quadrics, then it will be defined by such an ideal. And from this ideal, you just reconstruct the graph by drawing all the edges between monomials that you don't see.
Subspace arrangement means
a union of subspaces, coordinate subspaces. So coordinate subspaces means, right, you just get them in projective setting, you just get them by setting some coordinates to 0. Okay? And what does a quadratic form in this coordinate ring look like? Well, these monomials correspond to very special symmetric matrices. So xi, xj, maybe make it 2, corresponds to the symmetric matrix where you put a 1 in the ijth entry and zeros everywhere else. So reading a quadratic form modulo this monomial means you read the matrix modulo this matrix. So you get to pick this ijth entry to be whatever you want it to be. So it's really a matrix completion problem. Okay? Does that make sense? So what happens in our example? So if G is the 4 cycle, and I restrict the quadratic form to these 4 lines. So if I restrict to this line, I will see a quadratic form that only involves the first 2 variables. So for the matrix, that means I only observe this block. Because all the other monomials I don't see, because x3 is 0 or x4 is 0 on this line. So if I just look at the line spanned by E1 and E2, if I restrict my quadratic form to this line, it means I just look at this 2 by 2 block. And the same is true for the other lines, right? So this is the restriction to the line spanned by the 2nd and 3rd coordinate vector, 3rd and 4th, and then there's 1 and 4, which will give me this 2 by 2 block. And I will never observe these entries because they correspond to the 2 monomials in my ID. Okay, so if I want to write this as a sum of squares, though, I will have to fill these in such that this is a PSD matrix. Okay? All right. Any questions? All right. So this is one of the motivations why we looked at reducible sets and sets, so generalized from irreducible projective varieties to reducible real algebraic sets, because we might want to do matrix completion, for example. And the theorem that you can prove, so this is with Greg and Mauricio Velasco. So, let's recall. So, X is a totally real algebraic set. It sits inside Pn. Needs to be non-degenerate. That's it, I think. Okay. So totally real means in the setup, so if you look at each irreducible component, then each irreducible component should have a smooth real point. That's sort of one definition of what totally real means. So you want the real points to really see what this set is. In other words, okay. And these 2 cones are the same. So every non-negative polynomial is a sum of squares on the set if and only if x is 2 regular. So I mean Castelnuovo-Mumford regularity. So the free resolution is linear.
Only for this kind of arrangement?
No, this is any total. So needs to be defined by real polynomials.
Mm-hmm.
And every irreducible component needs to have a smooth real point. So in particular, coordinate subspace arrangements are fine because the irreducible components are subspaces and all the subspaces have smooth real points. Oh, there's a slightly more general statement.
We use so then we can say that this is minimal, but it is not irreducible.
This generalizes varieties of minimal degree. So if you're irreducible, then you are 2 regular if and only if you're a variety of minimal degree. Sort of the degree, there's no reasonable inequality between degree and codimension if you have a reducible thing. So That's sort of the correct way to generalize this inequality to reducible things. Okay. Okay.
What the Aij stands for?
These will be the coefficients of a quadratic form. So if you take, so this is an example of the 4-cycle. So you restrict the quadratic form to this arrangement of 4 lines. Then it corresponds to a symmetric matrix, and this is the symmetric matrix you will see.
He's just saying that if you look at this matrix and you see that the 2 by 2 minors are positive semi-definite, right? That's what it means to be non-negative. And then, but then he's asking, but is it true that I can complete it to globally positive semi-definite matrices? And the theorem says that this can happen if your underlying already X was too regular, which for graphs also has a meaning, as Rainer explained last time.
That's what I just wanted to mention. So I mentioned these 2 other results last time. So there's this completion theorem, Groen-Johnson, Saar and Volkowitz, that says, now I can phrase it in this way. So if you have G a graph, and Pxg is equal to if and only if G is chordal. So if you want to do a matrix completion problem, so if you want to complete, suppose I give you the Aij, and you want to complete this matrix to a PSD matrix, then everything you see needs to be PSD. So I see already this 2 by 2 block. And if the whole matrix is supposed to be positive semi-definite, this 2 by 2 block needs to be positive semi-definite. What that means is if you write this as a sum of squares, you can extend it to a globally positive semi-definite quadratic form. If you restrict to a line, it better be also a non-negative polynomial. So that's sort of the obvious necessary condition if you want to do positive semi-definite completion. All the completely specified matrices need to be PSD, and they observe that this is enough, that these are all the conditions, if and only if you have a chordal graph. So if the pattern of missing entries is very special. So chordal means, G has no induced cycles of length greater than or equal to 4. So this is not a chordal graph. In this case, it's not enough just to look at these 2 by 2 blocks. There are more conditions on a matrix to have a positive semi-definite completion. Okay, so if you combine these 2 theorems, then you see that Xg, so such a subspace arrangement, is 2 regular if and only if the graph is chordal, and that was a known theorem that I also mentioned last time due to Fröberg. So if G is a graph, then this square-free monomial ideal is 2 regular if and only if G is chordal. So these 3 theorems connect all these 3 conditions. This being equal, the graph being chordal, and the ideal being 2 regular. So all these 3 conditions are connected by one of these theorems. Okay. Any questions? So far, so good. So far. Okay, so my goal today is at least to give you a hint of how you go from such a condition to the free resolution. So how these things are related. And the thing, so one of the main steps is convex duality that Greg explained. briefly in this talk. So instead of looking at these cones, we look at their convex dual cones. So it's a fact that is not hard to check that under these assumptions, these two cones are the same if their projective dual cones are the same. If they're, what did I say? Convex dual cones is what I need to say. Okay, so what are these? Well, by definition, maybe let's just write it down once. So if you have a convex cone in some Euclidean space, then its dual is the set of all supporting hyperplanes. So formally, you take all linear forms, or linear functionals rather, on Rn that contain the cone in one of their half spaces. So what I'm saying is, so this is L of x is equal to 0 is a hyperplane, and greater than or equal to 0 means you just look at one side, and I'm saying the cone is contained in this half space. And you collect all of these linear forms, and that thing makes the dual convex cone. And then it's one of the corollaries of the separation theorem that you have convex biduality. So if you do this twice, you get your cone back. So that's the separation theorem. Should I keep this one? Well, no. So if the cone is nice, so you need a closed and you need a closed cone. So closed in the usual Euclidean topology. And that's how you get this equivalence. That's convex biduality, because these cones are closed and nice. If the dual cones are the same, the primal cones are the same by double dualizing. Okay, so, and I claim that these are sort of algebraically nicer. So what are they? So the dual cone to the cone of non-negative polynomials are all linear forms that are non-negative on non-negative polynomials. And you can certainly give me some. I'm sure you can name one linear functional that's non-negative on non-negative polynomials. I'm sure you can find one. Oh, that is true. But I'm looking for a simpler one. So if you take a positive measure, you can take a point measure, for example, right? So, and a point measure is a point evaluation. So if you evaluate at any real point, this will be a linear functional, and it will certainly be non-negative or non-negative polynomials. But by convex biduality, that is exactly what it is. So the dual cone is the cone generated by point evaluations. And that you can see by duality. If you take the dual cone to whatever this is, then you will exactly recover the condition that you're a non-negative polynomial because you evaluate it at every point and you got a non-negative number. So by convex biduality, this cone is really just generated by point evaluations. Okay. So the dual cone to sums of squares is also nice. Let me see, what are we going to say? Okay, let's not do this yet. So let's observe. You have this inclusion of cones, but if you think about it, if you take dual cones, you will reverse the inclusion Why is that? Because if you have a cone, if you have a linear functional that's non-negative on the larger cone, it will certainly be non-negative on the smaller cone. So you reverse inclusion. And this one we understand. This is the cone generated by point evaluations. So a question that we ask, what is this cone minimally generated by? So in terms of convex geometry, I'm asking what are the extreme rays of this cone. So this is the cone generated by what? That is the question. And these things that should go there are called extreme rays. So really I'm looking for a minimal generating set for this cone. Okay. So far so good?
There is a theorem that such a notion makes sense.
Sure. There are some theorems. So a theorem is that such a minimal generating set that is smaller than this cone exists. There is a nice one. It's Minkowski's theorem, I guess. There's a unique and nice one. Okay. So now we know what this cone is. So question, what is the dual cone to sums of squares? And that one, you know, it's a bit more complicated. Let's see. So it's the set of all linear functionals that are non-negative on sums of squares. That's the same as saying that they are non-negative on squares by linearity of this thing. So if you're non-negative on squares, you're non-negative on sums of squares. But this one, so the trick is that to every such L we associate, well, we look at its catalecticant matrix that I like to write down like this. So it's a bilinear form. We turn this linear functional into a bilinear form. Fg gets mapped to L of f times g. And then being non-negative on squares means if you plug in f comma f, you always get a non-negative number. It means that this bilinear form is a positive semi-definite bilinear form. So this is the, we like to call it Hankel matrix. Oh dear. Other people like to call it moment matrix or catalecticant, so they're all the same. So this is what we call a spectrahedral cone. So what does that mean? That means you take positive semi-definite matrices. That's the condition. This matrix is positive semi-definite, but you don't look at all of them, but just a linear space of them. So there is some linear space, namely, you know, you need to mod out by everything that's identically zero on the ideal. So this is what we call a spectrahedron. And it's the convex geometry of spectrahedra that allow us to connect extreme rays of this cone to algebraic properties that you can then investigate with free resolutions. So what happens? Any questions so far before I tell you the crucial observation?
What's L?
L is a, you know, it's some linear space that has to do with the ideal defining your variety. You know, so the coordinate ring is a projection. Right, so R2 is the projection of quadratic forms. There's some kernel, and this L is sort of the orthogonal complement to this kernel. So it's Depends on the ideal, what this L is. Okay, so the crucial observation that Greg made some time ago is the following. If you take an extreme ray of such a spectrahedron, I'm talking about rays, so this should be a ray. Then so you can characterize this in terms of the kernel of the catalectican matrix. So given this extreme ray, I will build, well, I will just take the kernel, which will be a bunch of linear forms. Kernel are some linear forms, and these linear forms are very special. So this is a base point free linear series on X. Okay, I forgot an assumption, so this better not be a point evaluation. You need to, if it is a point evaluation, then this is just the set of all linear forms that are zero at that point. So they are certainly not base point free, right? But as soon as this is not a point evaluation, which is the one we care about, then this will be a base point free linear series, and if you look at, call it W, if you look at what it generates in degree 2, and this will be a hyperplane. And the linear functional vanishing on this is the L you started with. Okay? So it can generate more. L will certify that it can't generate more than a hyperplane. The condition is that it's actually equal to this hyperplane defined by L. So this one will be, what do I call this? V of L maybe? Is that confusing? So that's the same L you start with. Okay. So that's the characterization. So in particular, we get this base point free linear series. That is what algebraically is the interesting thing that you can use.
Sorry, so here we regard BL as a map from R1 to R1 dual, yes?
I look at it as a matrix and I take its right kernel, for example. It's symmetric. You can also take its left kernel. Okay. Good. So if you wonder what can these extreme rays be, you might wonder what are these linear series. And that is what we sort of call the P base point free property. So let me define what I mean. So we say that this algebraic set X satisfies the P base point free property if every linear series of codimension at most P generates R2. Yes. Otherwise there is no chance that every base point free codimension at most P generates R2. So meaning these kernels cannot exist. because there are no base point free linear series that generate the hyperplane, all of them generate everything. So sort of, if you have the p base point free property, there exists no extreme rays that have catalecticant matrices of rank p. And that's why we take the codimension. Codimension of the kernel is the rank of the matrix. That's why we chose to state it in terms of codimension. Okay. So then how good is this number in detecting the correct ranks of these? And the answer is sometimes that's pretty good. And the rank of these things we call the Hankel index. So this one is the smallest p. Such that there exists an extreme ray of sigma x that is not a point evaluation of rank p. So we would like these two numbers to be the same. If you have an extreme ray of rank p, or I mean off by 1, not the same. If you have an extreme ray of rank p, it will produce a base point free linear series of codimension p, which will generate a hyperplane, and this should be off by 1 from the p base point free property. That's what we would like to be true. So if you pick a p such that you know that there exists a base point free linear series of codimension p that does not generate everything, then we would like there to be an extreme ray. It's sort of the idea. And the theorem is that this, so first of all, what we can prove, so that's a simple consequence of Greg's observation. So if x is nice, then this p plus 1 gives a lower bound on this. So what you need is x totally real algebraic set, non-degenerate, non-degenerate. You need defined by quadrics. Then the Hankel index is at least p plus 1 if x has the p base point free property. And that's a direct consequence of Greg's observation. So if all of the base point free linear series of codimension p generate everything, then there cannot be an extreme ray of rank p, because that certifies that there is a base point free linear series that generates only a hyperplane. So this inequality, is Greg's observation basically. All right. And so this p base point free property is related to free resolutions. It's related to the length of the linear strand. So it's related to property n2p. Okay, so minimal free resolution. So I will just quickly recall what that means. Or does everybody know what property N2P is? So there are at least some people who know this better than I do. Right, so you resolve the defining ideal. And then you have property N2P. If I of x is generated by quadrics. And the degree of phi I is equal to 1 for some indices. So let's see, for I is equal to 1 up to p minus, the way I wrote it down. So these syzygies are linear for a while. And to p measures how long. Okay. And then the theorem we use to relate the free resolution to the base point free property is due to Eisenbach, Hunecke, and Ulrich. And they prove if x satisfies N2P, then x has the P base point free property. And I know no easy proof of this result. So they prove this as a corollary in a paper where they study slightly different questions. And then this sort of falls out. It's a local cohomology paper. And then this is a corollary to their work, but I don't know a good and simple reason why the free resolution detects the codimension of linear series that generate everything in degree 2. I don't know if there's an elementary or at least a more accessible proof than the one they gave. So theirs is they use heavy machinery.
They use Locke-Moore proof?
Yes. They study the regularity of Tor. And then it falls out in one of the last sections where they talk about applications of their results.
We have super proof of this.
Good.
Yeah.
Good. I was not aware. Maybe. Need to understand. Okay. So, but then, sort of, what does that mean? So, one implication of this, for example, if you're too regular, then you have the p base point free property for every p. So corollary, if x is too regular, then there are no possible ranks for extreme rays that are not point evaluations. So there are no extreme rays of sigma x star that are not point evaluations. Well, this is a complicated way of saying that the cones are the same. So that's one direction of our theorem. If you have the p base point free property for every p, then there's no possible rank this one can have. So all of them are point evaluations. So these two cones are the same. As I explained, by convex biduality, that gives one implication in the theorem I stated. Okay. All right, so the reverse implication I will not talk about. So that the reverse we basically prove by induction. So what we do is project away from points and show that that this condition is preserved under projection, and then you can sort of do. Okay. It was faster than I thought it would be. Okay, so I have a question for you. So, let me state this carefully. I would like to know if the free resolution, and if so how, can detect the first time. So, resolution, the p base point free property. So, the codimension of a linear series, a base point free linear series that generates R2. So, this the highest codimension, or the smallest dimension. Can the free resolution tell me the smallest k such that there exists W in R1 of dimension k? Now I'm saying it the wrong way. No, it's okay. Of dimension k with it generates R2.
Oh, wait.
The smallest, such that there is one that generates R2.
That's a different question from base point free property.
Yes, it's a different one. So we can maybe detect the p base point free property. So this other implication isn't always true, but at least, you know. But can we also detect this number? I also care about this number for other reasons. Let me explain why I like this number. I already like, argue, I don't know, what your opinion is on square free monomial ideals. If they are harder or easier, I don't know. But so for square free monomial ideals that are generated by quadrics, I like this number very much because it's the generic completion rank. So let me tell you, generic completion rank. If, whatever, you can make sense of this all the time. So let me sort of tell you what I mean. So R2 is the image of quadratic forms when you mod out by the degree 2 part of the ideal, right? So this is quadratic forms. So if you mod out by the ideal, you get the coordinate ring. Okay. So what I want to know, in here you have the variety of rank k. K quadratic forms. Now if you map, you take the projection of this variety. What I want to know is sort of when is this dominant map. So if you think about what it means to project this, so it's easier to think about what it means to project the tangent space. So if you pick a point, maybe we should discuss this. And you can write A as a sum of k squares. Either, pick a PSD point, then these things are real, or, whatever, pick any point, then these are complex. But you can write it as a sum of k squares. So what's the tangent space? So I claim that you can identify the tangent space with the sum of the h times li HI, Li, where HI are linear forms. So this is exactly the ideal generated by the Li in degree 2. So for example, that follows from Tarantini's lemma or something. Or you just differentiate this thing, you know. Anyway, so that's the tangent space. And so if I want this to be dominant, then there better be a tangent space that surjects onto this. That's the same as saying this linear series generates the coordinate ring in degree 2. So the existence of a linear series that generates R2 is the same as saying that this map is dominant. If and only if there exists linear series W such that W2 is equal to R2. Okay. So the smallest k such that such a thing exists is the smallest k such this projection is dominant. And this projection being dominant means I can complete almost all matrices that you give me there to a rank k matrix. If you give me the restriction of a quadratic form to x, a generic one, then I will be able to find a rank k preimage. So if you think about matrix completion problem, if we go back to the case where this is a square-free monomial ideal, and we're doing matrix completion, it really tells me a generic matrix has a completion of rank k. And that number seems to be not so easy to detect for even given the combinatorics of the graph. Say, you know, I give you the graph, tell me what is the smallest k such that this is dominant, seems to be a complicated question. So even in the, I mean, maybe not even, but in the case of quadratic square-free monomial ideals, this is a particularly nice number. So in general, it means that the minimal, well, the generic complex rank, which is also the minimal real rank, minimal typical real rank of a point is equal to k. So at least you would detect the minimal rank with respect to the variety of squares. Minimal typical real rank. All right. That's the open question I will leave you with. Thank you.
At least just x contain quadratic, right?
Yes, x defined by quadrics. We want to assume that x is cut out by quadrics. Also feel free to use any other tool. Not the free resolution, but anything else you can find. So. But maybe the free resolution can help, I don't know.